Chapter 1 Some Basic Concepts of Chemistry. Chemistry is the science of molecules and their transformations. It is the science not so much of the 100 elements but of the infinite variety of molecules that may be built from them. Roald Hoffmann. Science can be viewed as a continuing human effort to systemize knowledge for describing and understanding nature. You have learned in your previous classes that we come across diverse substances present in nature and changes in them in daily life. Curd formation from milk, formation of vinegar from sugarcane juice, on keeping for prolonged time and rusting from iron are some of the examples of changes which we come across many times. For the sake of convenience, science is subdivided into various disciplines: chemistry, physics, biology, geology, etc. The branch of science that studies the preparation, properties, structure, and reactions of material substances is called chemistry. Development of chemistry. Chemistry is, as we understand it today, is not a very old discipline. Chemistry was not studied for its own sake. Rather, it came up as a result of search for two interesting things. One, philosopher's stone or paras, which would convert all baser metals, example iron and copper, into gold. Elixir of life, which would grant immortality. People in ancient India already had the knowledge of many scientific phenomena much before the advent of modern science. They applied that knowledge in various walks of life. Chemistry developed many in form of alchemy and iatrochemistry during 1300 to 1600 CE. Modern chemistry took shape in the 18th century Europe after a few centuries of chemical traditions which were introduced in Europe by the Arabs. Other cultures, especially the Chinese and the Indian, had their own alchemical traditions. These included much knowledge of the chemical processes and techniques. In ancient India, chemistry was called Rasayan Shastra, Rastantra, Raskriya or Rasvidya. It included metallurgy, medicine, manufacture of cosmetics, glass, dyes, etc. Systematic excavations at Mohenjo-daro in Sindh and Harappa in Punjab prove that the story of development of chemistry in India is very old. Archaeological findings show that baked bricks were used in construction work. It shows the mass production of pottery, which can be regarded as the earliest chemical process in which materials were mixed, molded, and subjected to heat by using fire to achieve desirable qualities. Remains of glazed pottery have been found in Mohenjo-daro. Gypsum cement has been used in construction work. It contains lime sand and traces of CaCO3. Harappans made faience, a sort of glass, which was used in ornaments. They melted and forged a variety of objects from metals such as lead, silver, gold, and copper. They improved the hardness of copper for making artifacts by using tin and arsenic. A number of glass objects were found in Maski in South India 1000 to 900 BCE and Hastinapur and Taxila in North India 1000 to 200 BCE. Glass and glazes were colored by addition of coloring agents like metal oxides. Copper metallurgy in India dates back to the beginning of Chalcolithic cultures in the subcontinent. There are much archaeological evidences to support the view that technologies for extraction of copper and iron were developed indigenously. According to Rig Veda, tanning of leather and dyeing of cotton were practiced during 1000 to 400 BCE. The golden gloss of the black polished ware of northern India could not be replicated and is still a chemical mystery. These wares indicate the mastery with which keen temperatures could be controlled. Kautilya's Arthashastra describes the production of salt from sea. A vast number of statements and material described in ancient Vedic literature can be shown to agree with modern scientific findings. Copper utensils, iron, gold, silver ornaments, and terracotta discs and painted grey pottery have been found in many archaeological sites in North India. Sushruta Samhita explains the importance of alkalis. The Charaka Samhita mentions ancient Indians who knew how to prepare sulfuric acid, nitric acid, and oxides of copper, tin, and zinc, the sulfates of copper, zinc, and iron, and the carbonates of lead and iron. Rasopanishada describes the preparation of gunpowder mixture. Tamil texts also describe the preparation of fireworks using sulfur, charcoal, saltpeter, that is potassium nitrate, mercury, camphor, etc. Nagarjuna was a great Indian scientist. He was a reputed chemist, an alchemist, and a metallurgist. His work, Ras Ratnakar, deals with the formulation of mercury compounds. He has also discussed methods for the extraction of metals like gold, silver, tin, and copper. The book Sarnavam appeared around 800 CE. It discusses the uses of various furnaces, ovens, and crucibles for different purposes. It describes methods by which metals could be identified by flame color. Chakrapani discovered mercury sulfide. The credit for inventing soap also goes to him. He used mustard oil and some alkalis as ingredients for making soap. Indians began making soap in the 18th century CE. Oil of Iranda and seeds of mahua plant and calcium carbonate were used for making soap. The painting found on the walls of Ajanta and Ellora, which look fresh even after ages, testify to a high level of science achieved in the ancient India. Varamihir's Brihad Samhita is a sort of encyclopedia, which was composed in the 6th century CE. It informs about the preparation of glutinous material to be applied on walls and roofs of houses and temples. It was prepared entirely from extracts of various plants, fruits, seeds, and barks, which were concentrated by boiling and then treated with various resins. It will be interesting to test such materials scientifically and assess them for use. Importance of chemistry. Chemistry plays a central role in science and is often intertwined with other branches of science. Principles of chemistry are applicable in diverse areas such as weather patterns, functioning of brain, and operation of computer. Production in chemical industries, manufacturing fertilizers, alkalis, acids, salts, dyes, polymers, drugs, soaps, detergents, metals, alloys, etc., including new material. Chemistry contributes in a big way to the national economy. It plays an important role in meeting human needs for food, healthcare, products, and other material aimed at improving the quality of life. This is exemplified by the large-scale production of a variety of fertilizers, improved variety of pesticides and insecticides. Chemistry provides methods for isolation of life-saving drugs from natural sources and makes possible synthesis of such drugs. Some of these drugs are cisplatin and Taxol, which are effective in cancer therapy. The drug AZT, azithromycin, is used for helping AIDS patients. Chemistry contributes to a large extent in the development and growth of a nation. With a better understanding of chemical principles, it has now become possible to design and synthesize new material having specific magnetic, electric, and optical properties. This has led to the production of superconducting ceramics, conducting polymers, optical fibers, etc. Chemistry has helped in establishing industries which manufacture utility goods like acids, alkalis, dyes, polymers, metals, etc. These industries contribute in a big way to the economy of a nation and generate employment. In recent years, chemistry has helped in dealing with some of the pressing aspects of environmental degradation. with a fair degree of success. Safer alternatives to environmentally hazardous refrigerants and like CFCs, chlorofluorocarbons responsible for ozone depletion in the stratosphere have been successfully synthesized. However, many big environmental problems continue to be matters of grave concern to the chemists. One such problem is the management of greenhouse gases like methane, carbon dioxide, etc. Understanding of biochemical processes, use of enzymes for large-scale production of chemicals and synthesis of new exotic material are some of intellectual challenges for the future generation of chemists. A developing country like India needs talented and creative chemists for accepting such challenges. To be a good chemist and to accept such challenges, one needs to understand the basic concepts of chemistry, which begin with the concept of matter. Let us start with the nature of matter. The nature of matter. You are already familiar with the term matter from your earlier classes. Anything which has mass and occupies space is called matter. Everything around us, for example, book, pen, pencil, water, air, all living beings, etc., are composed of matter. You know that they have mass and they occupy space. Let us recall the characteristics of the states of matter which you learned in your previous classes. States of matter. You are aware that matter can exist in three physical states, that is, solid, liquid, and gas. The constituent particles of matter in these three states can be presented as shown in figure 1.1. Particles are held very close to each other in solids in an orderly fashion, and there is not much freedom of movement. In liquids, the particles are close to each other, but they can move around. However, in gases, the particles are far apart as compared to those present in solid and liquids, and their movement is easy and fast. Because of such arrangement of particles, different states of matter exhibit the following characteristics. Solids have definite volume and definite shape. Liquids have definite volume but do not have definite shape. They take the shape of the container in which they are placed. Gases have neither definite volume nor definite shape. They completely occupy the space in the container in which they are placed. These three states of matter interconvertible by changing the conditions of temperature and pressure. On heating, a solid usually changes to a liquid, and the liquid further on heating changes it to a gas or vapor. In the reverse process, a gas on cooling liquefies to the liquid, and the liquid on further cooling freezes to the solid. Classification of matter. In class 9 chapter 2, we have learned that at the macroscopic or bulk level, matter can be classified as a mixture or pure substance. This can be further subdivided as shown in figure 1.2. When all constituent particles of a substance are same in chemical nature, it is said to be pure substance. A mixture contains many types of particles. A mixture contains particles of two or more pure substances which may be present in it in any ratio. Hence, their composition is variable. Pure substances forming mixture are called its components. Many of the substances present around you are mixtures. For example, sugar solution in water, air, tea, etc. are all mixtures. A mixture may be homogeneous or heterogeneous. In a homogeneous mixture, the components completely mix with each other. This means particles of components of the mixture are uniformly distributed throughout the bulk of the mixture and its composition is uniform throughout. Sugar solution and air are the examples of homogeneous mixtures. In contrast to this, in a heterogeneous mixture, the composition is not uniform throughout and sometimes different components are visible. For example, mixtures of salt and sugar, grains and pulses along with some dirt, often stone pieces, are heterogeneous mixtures. You can think of many more examples of mixtures which you come across in daily life. It is worthwhile to mention here that the components of a mixture can be separated by using physical methods such as simple hand picking, filtration, crystallization, distillation, etc. Pure substances have characteristics different from mixtures. Constituent particles of pure substances have fixed composition. Copper, silver, gold, water, and glucose are some examples of pure substances. Glucose contains carbon, hydrogen, and oxygen in a fixed ratio, and its particles are of same composition. Hence, like all other pure substances, glucose has a fixed composition. Also, its constituents carbon, hydrogen, and oxygen cannot be separated by simple physical methods. Pure substances can further be classified into elements and compounds. Particles of an element consist of only one type of atoms. These particles may exist as atoms or molecules. You may be familiar with atoms and molecules from the previous classes. However, you will be studying about them in detail in Unit 2. Sodium, copper, silver, hydrogen, oxygen, etc. are some examples of elements. All atoms are of one type. However, the atoms of different elements are different in nature. Some elements such as sodium and copper contain atoms as their constituent particles, whereas in some others the constituent particles are molecules which are formed by two or more atoms. For example, hydrogen, nitrogen, and oxygen gases consist of molecules in which two atoms combine to give their respective molecules. This is illustrated in figure 1.3. When two or more atoms of different elements combine together in a definite ratio, the molecule of a compound is obtained. Moreover, the constituents of a compound cannot be separated into simpler substances by physical methods. They can be separated by chemical methods. Example of some compounds are water, ammonia, carbon dioxide, sugar, etc. The molecules of water and carbon dioxide are represented in figure 1.4. Note that a water molecule comprises two hydrogen atoms and one oxygen atom. Similarly, a molecule of carbon dioxide contains two oxygen atoms combined with one carbon atom. Thus, the atoms of different elements are present in a compound in a fixed and definite ratio, and this ratio is characteristic of a particular compound. Also, the properties of a compound are different from those of its constituent elements. For example, hydrogen and oxygen are gases, whereas the compound formed by their combination, that is water, is a liquid. It is interesting to note that hydrogen burns with a pop sound and oxygen is a supporter of combustion, but water is used as a fire extinguisher. Properties of matter and their measurement. Physical and chemical properties. Every substance has unique or characteristic properties. These properties can be classified into two categories: physical properties such as color, odor, melting point, boiling point, density, etc., and chemical properties like composition, combustibility, reactivity with acids and bases, etc. Physical properties can be measured or observed without changing the identity or the composition of the substance. The measurement or observation of chemical properties requires a chemical change to occur. Measurement of physical properties does not require occurrence of a chemical change. The examples of chemical properties are characteristic reactions of different substances. These include acidity or basicity, combustibility, etc. Chemists describe, interpret, and predict the behavior of substances on the basis of knowledge of their physical and chemical properties, which are determined by careful measurement and experimentation. In the following section, we will learn about the measurement of physical properties. Measurement of physical properties. Quantitative measurement of properties is required for scientific reinvestigation. for scientific investigation. Many properties of matter such as length, area, volume, etc. are quantitative in nature. Any quantitative observation or measurement is represented by a number followed by units in which it is measured. For example, length of a room can be represented as 6 meter. Here 6 is the number and denotes meter, the unit in which the length is measured. Earlier, two different systems of measurement, that is the English system and the metric system, were being used in different parts of the world. The metric system, which originated in France in late 18th century, was more convenient as it was based on the decimal system. Latter need of a common standard system was felt by the scientific community. Such a system was established in 1960 and is discussed in detail below. International System of Units or SI. The International System of Units, in French, Les Systèmes Internationaux d'Units, abbreviated as SI, was established by the 11th General Conference on Weights and Measures, CGPM, from Conference Generale des Poids et Measures. The CGPM is an intergovernmental treaty organization created by a diplomatic treaty known as Meter Convention, which was signed in Paris in 1875. The SI system has 7 base units and they are listed in table 1.1. These units pertain to the 7 fundamental scientific quantities. The other physical quantities such as speed, volume, density, etc. can be derived from these quantities. Maintaining the national standards of measurement. The system of units, including unit definitions, keep on changing with time. Whenever the accuracy of measurement of a particular unit was enhanced substantially by adopting new principles, member nations of Meter Treaty, signed in 1875, agreed to change the formal definition of that unit. Each modern industrialized country, including India, has a National Metrology Institute, NMI, which maintains standards of measurements. This responsibility has been given to the National Physical Laboratory, NPL, New Delhi. This laboratory establishes experiments to realize the base units and derived units of measurement and maintains national standards of measurement. These standards are periodically intercompared with standards maintained at other national metrology institutes in the world, as well as those established at the International Bureau of Standards in Paris. The definition of the SI base units are given in table 1.2. The SI system allows the use of prefixes to indicate the multiples or submultiples of a unit. These prefixes are listed in table 1.3. Let us now quickly go through some of the quantities which you will be often using in this book. Unit of length meter, unit of mass kilogram, unit of time second, unit of electric current ampere, unit of thermodynamic temperature Kelvin, unit of amount of substance mole, unit of luminous intensity candela. Mass and weight. Mass of a substance is the amount of matter present in it, while weight is the force exerted by gravity on an object. The mass of a substance is constant, whereas its weight may vary from one place to another due to change in gravity. You should be careful in using these terms. The mass of a substance can be determined accurately in the laboratory by using an analytical balance. The SI unit of mass as given in table 1.1 is kilogram. However, its fraction named as gram, 1 kg is equal to 1000 gram, is used in laboratories due to smaller amounts of chemicals used in the chemical reactions. Volume. Volume is the amount of space occupied by the substance. It has a units of length to the power 3. So, in SI system, volume has the unit of meter cube. But again, in chemistry laboratories, smaller volumes are used. Hence, volume is often denoted by centimeter cube or decimeter cube units. A common unit, liter. which is not an SI unit, is used for measurement of volume of liquids. 1 liter is equal to 1000 milliliter. 1000 centimeter cube is equal to 1 decimeter cube. Figure 1.6 helps to visualize these relations. In the laboratory, the volume of liquids or solutions can be measured by graduated cylinder, burette, pipette, etc. A volumetric flask is used to prepare a known volume of a solution. These measuring devices are shown in figure 1.7. Density. Two properties, mass and volume, discussed above are related as follows. Density is equal to mass by volume. Density of a substance is its amount of mass per unit volume. So, SI unit of density can be obtained as follows. SI unit of density is equal to SI unit of mass divided by SI unit of volume, which is equal to kg by meter cube or kg per meter cube. This unit is quite large, and a chemist often expresses density as gram per centimeter cube, where mass is expressed in gram and volume is expressed in centimeter cube. Density of a substance tells us about how closely its particles are packed. If density is more, it means particles are more closely packed. Temperature. There are three common scales to measure temperature: degree centigrade or degree Celsius, degree Fahrenheit, and Kelvin. Here, K is the SI unit or Kelvin is the SI unit. The thermometers based on these scales are shown in figure 1.8. Generally, the thermometer with Celsius scale are calibrated from 0 degree to 100 degree, where these two temperatures are freezing and boiling point of water respectively. The Fahrenheit scale is represented between 32 to 212 degrees. Temperature on two scales are related to each other by the following relationship. Degree Fahrenheit is equal to 9 by 5 degrees Celsius plus 32. The Kelvin scale is related to Celsius scale as follows. Kelvin is equal to degree Celsius plus 273.15. It is interesting to note that temperature below 0 degree centigrade, that is negative values, are possible in Celsius scale, but in Kelvin scale, negative temperature is not possible. Uncertainty in measurement. Many a times in the study of chemistry, one has to deal with experimental data as well as theoretical calculations. There are meaningful ways to handle the numbers conveniently and present the data realistically with certainty to the extent possible. These ideas are discussed below in detail. As chemistry is the study of atoms and molecules which have extremely low masses and are present in extremely large numbers, a chemist has to deal with numbers as large as 602, 200, 000, 000, 000 for the molecules of 2 gram of hydrogen gas, or as small as 0.000000000000000000166 gram mass of each atom. Similarly, other constants such as Planck's constant, speed of light, charges of particles, etc. involve numbers of the above magnitude. They may look funny for a moment to write or count numbers involving so many zeros, but it offers a real challenge to do simple mathematical operations of addition, subtraction, multiplication or division with such numbers. You can write any two numbers of the above type and try any one of the operation you like to accept as a challenge, and then you will really appreciate the difficulty in handling such numbers. This problem is solved by using scientific notation for such numbers, that is, exponential representation in the form n into 10 to the power n, where small n is an exponent having positive or negative values and capital N is a number called digit term. which varies between 1.000 and 9.999. Thus, we can write 232.508 as 2.32508 into 10 to the power 2 in scientific notation. Note that while writing it, the decimal had to be moved to the left by 2 places, and same is the exponent 2 of 10 in the scientific notation. Similarly, 0.00016 can be written as 1.6 into 10 to the power minus 4. Here, the decimal has to be moved 4 places to the right, and minus 4 is the exponent in the multiplication and division. These two operations follow the same rules which are there for exponential numbers, that is, addition and subtraction. For these two operations, first the numbers are written in such a way that they have same exponent. After that, the coefficients, digit terms are added or subtracted as the case may be. Thus, for adding 6.65 into 10 to the power 4 and 8.95 into 10 to the power 3, exponent is made same for both the numbers. Thus, we get 6.65 into 10 to the power 4 plus 0.895 into 10 to the power 4. Then these numbers can be added as follows: 6.65 plus 0.895 whole into 10 to the power 4, which is equal to 7.545 into 10 to the power 4. Similarly, the subtraction of two numbers can be done as shown. Significant figures. Every experimental measurement has some amount of uncertainty associated with it because of limitation of measuring instrument and the skill of the person making the measurement. For example, mass of an object is obtained using a platform balance and it comes out to be 9.4. On measuring the mass of this object on an analytical balance, the mass obtained is 9.4213 grams. The mass obtained by an analytical balance is slightly higher than the mass obtained by using a platform balance. Therefore, digit 4 placed after decimal in the measurement by platform balance is uncertain. The uncertainty in the experimental or the calculated values is indicated by mentioning the number of significant figures. Significant figures are meaningful digits, which are known with certainty plus 1, which is estimated or uncertain. The uncertainty is indicated by writing the certain digits and the last uncertain digit. Thus, if we write a result as 11.2 ml, we say the 11 is certain and 2 is uncertain, and the uncertainty would be plus or minus 1 in the last digit. Unless otherwise stated, an uncertainty of plus minus 1 in the last digit is always understood. There are certain rules for determining the number of significant figures. These are stated below. All non-zero digits are significant. For example, in 285 cm, there are 3 significant figures, and in 0.25 ml, there are 2 significant figures. Zeros preceding to first non-zero digit are not significant. Such zero indicates the position of decimal point. The 0.03 has one significant figure and 0.0052 has two significant figures. Zeros between two non-zero digits are significant. Thus, 2.005 has four significant figures. Zeros at the end or right of a number are significant, provided they are on the right side of the decimal point. For example, 0.200 gram has 3 significant figures, but if otherwise the terminal zeros are not significant. If there is no decimal point, for example, 100 has only one significant figure, but 100 has 3 significant figures, and 100.0 has 4 significant figures. Such numbers are better represented in scientific notation. We can express the number 100 as 1 into 10 to the power 2 for one significant figure and 1.0 into 10 to the power 2 for two significant figures and 1.00 into 10 to the power 2 for three significant figures. Counting the number of objects, for example 2 balls or 20 eggs, have infinite significant figures, as these are exact numbers and can be represented by writing infinite number of zeros after placing a decimal. That is, 2 is equal to 2.0000, 20 is equal to 20.00000. In numbers written in scientific notation, all digits are significant. That is, example 4.01 into 10 to the power 2 has 3 significant figures and 8.256 into 10 to the power minus 3 has 4 significant figures. However, one would always like the results to be precise and accurate. Precision and accuracy are often referred to while we talk about the measurement. Precision refers to the closeness of various measurements for the same quantity. However, accuracy is the agreement of a particular value to the true value of the result. For example, if the true value for a result is 2.00 gram and student A takes two measurements and reports results as 1.95 grams and 1.93 grams, these values are precise as they are close to each other but are not accurate. Another student B repeats the experiment and obtains 1.94 grams and 2.05 grams as the results for two measurements. These observations are neither precise nor accurate. When the third student C repeats the measurements and reports 2.01 grams and 1.99 gram as a result, these values are both precise and accurate. This can be more clearly understood from the given data. Tip: addition and subtraction of significant figures. The result cannot have more digits to the right of the decimal point than either of the original numbers. Here, 18.0 has only one digit after the decimal point and the result should be reported only up to one digit after the decimal point, which is 31.1. Multiplication and division of significant figures. In these operations, the result must be reported with no more significant figures as in the measurement with the few significant figures. 2.5 into 1.25 is equal to 3.125. Since 2.5 has two significant figures, the result should not have more than two significant figures. Thus, it is 3.1. While limiting the result to the required number of significant figures as done in the above mathematical operation, one has to keep in mind the following points for rounding of the numbers. If the rightmost digit to be removed is more than 5, the preceding number is increased by 1. For example, 1.386. If we have to remove 6, we have to round it off to 1.39. If the rightmost digit to be removed is less than 5, the preceding number is not changed. For example, 4.334. If 4 is to be removed, then the result is rounded up to 4.33. The rightmost digit to be removed is 5, then the preceding number is not changed. If it is an even number but it is increased by 1, if it is an odd number, for example, if 6.35 is to be rounded off by removing 5, we have to increase 3 to 4, giving 6.4 as the result. However, if 6.25 is to be rounded off, it is 6.2. Dimensional analysis. Often while calculating, there is a need to convert units from one system to the other. The method used to accomplish this is called factor label method or unit factor method or dimensional analysis. This is illustrated below. Example, a piece of metal is 3 inch represented by IN long. What is its length in centimeter? Solution. We know that 1 in 1 inch is equal to 2.54 centimeter. From this equivalence, we can write 1 inch by 2.54 centimeter is equal to 1, which is equal to 2.54 centimeter by 1 inch. Both of these are called unit factors. If some number is multiplied by these unit factors, that is 1, it will not be affected otherwise. Say the 3 inch given above is multiplied by the unit factors. So 3 inch is equal to 3 into 2.54 centimeter by inch, which is equal to 3 into 2.54 centimeter, which is equal to 7.62 centimeters. Now, the unit factor by which multiplication is to be done is that unit factor 2.54 centimeter by 1 inch in the above case, which gives the desired units, that is, the numerator should have that part which is required in the desired result. It should also be noted in the above example that units can be handled just like other numerical part. It can be cancelled, divided, multiplied, squared, etc. Let us study one more example. Example: a jug contains 2 liters of milk. Calculate the volume of milk in meter cube. Since 1 liter is equal to 1000 centimeter cube and 1 meter is equal to 100 centimeter, which gives 1 meter by 100 centimeter equals to 1 is equal to 100 centimeter by 1 meter. To get meter cube from the above unit factors, the first unit factor is taken and it is cubed. Now 2 liter is equal to 2 into 1000 centimeter cube. The above is multiplied by the unit factor, this 2 into 10 to the power minus 3 meter cube. Another example, how many seconds are there in 2 days? Here we know 1 day is equal to 24 hours, then 1 hour is equal to 60 minutes. So for converting 2 days to seconds, that is 2 days is equal to dash seconds. The unit factor can be multiplied in series in one step only as follows: 2 day into 24 hour by 1 day into 60 minute by 1 hour into 60 second by 1 minute, which is equal to 2 into 24 into 60 into 60 is equal to 172800 seconds. Law of chemical combinations. The combination of elements to form compounds is governed by the following 5 basic laws. Law of conservation of mass. This law was put forth by Antony Lavoisier in 1789. He performed careful experimental studies for combustion reactions and reached to the conclusion that in all physical and chemical changes there is no net change in mass during the process. Hence, he reached to the conclusion that matter can neither be created nor destroyed. This is the law of conservation of mass. This law formed the basis for several later developments in chemistry. In fact, this was the result of exact measurement of masses of reactants and products and carefully planned experiments performed by Lavoisier. Law of definite proportions. This law was given by a French chemist, Joseph Proust. He stated that a given compound always contains exactly the same proportion of elements by weight. Proust worked with 2 samples of cupric carbonate, one of which was natural origin and the other was synthetic. He found that the composition of elements present in it was same for both the samples as shown below. Thus, he concluded that irrespective of the source, a given compound always contains same elements combined together in the same proportion by mass. The validity of this law has been confirmed by various experiments. It is sometimes also referred to as the law of definite composition. Law of multiple proportions. This law was proposed by Dalton in 1803. According to this law, if 2 elements can combine to form more than one compound, the masses of one element that combine with a fixed mass of the other element are in the ratio of small whole numbers. For example, hydrogen combines with oxygen to form 2 compounds, namely water and hydrogen peroxide. Hydrogen plus oxygen gives water, 2 gram, 16 gram, 18 gram. Hydrogen plus oxygen gives hydrogen peroxide, 2 gram, 32 gram, 34 grams. Here, the masses of oxygen 16 and 32, which combine with a fixed mass of hydrogen, bear a simple ratio 16:32 or 1:2. Gay-Lussac's law of gaseous volumes. This law was given by Gay-Lussac in 1808. He observed that when gases combine or are produced in a chemical reaction, they do so in a simple ratio by volume, provided all gases are at the same temperature and pressure. Thus, 100 ml of hydrogen combine with 50 ml of oxygen to give 100 ml of water vapor. Thus, the volumes of hydrogen and oxygen which combine, that is 100 ml and 50 ml, bear a simple ratio of 2:1. Gay-Lussac's discovery of integer ratio in volume relationship is actually the law of definite proportions by volume. The law of definite proportions stated earlier was the respect to mass. Gay-Lussac's law was explained properly by the work of Avogadro in 1811. Avogadro's law. In 1811, Avogadro proposed that equal volumes of all gases at the same temperature and pressure should contain equal number of molecules. Avogadro made a distinction between atoms and molecules, which is quite understandable in present times, if we consider again the reaction of hydrogen and oxygen to produce water. We see that 2 volumes of hydrogen combine with 1 volume of oxygen to give 2 volumes of water, without leaving any unreacted oxygen. Note that in figure 1.9 page 16, each box contains equal number of molecules. In fact, Avogadro could explain the above result by considering the molecules to be polyatomic. If hydrogen and oxygen were considered as diatomic as recognized now, then the above results are easily understandable. However, Dalton and others believed at that time that atoms of the same kind cannot combine and molecules of oxygen or hydrogen containing 2 atoms did not exist. Avogadro's proposal was published in the French journal de Physique. In spite of being correct, it did not gain much support. After about 50 years in 1860, the first international conference on chemistry was held in Karlsruhe, Germany, to resolve various ideas. At the meeting, Stanislaw Cannizzaro presented a sketch of a course of chemical philosophy, which emphasized on the importance of Avogadro's work.